All right. Good morning, everybody. Good to be back here, knowing we're here in the Department of Physical Astronomy where all the clocks are always some random numbers. So let's get started. You'd think in a physics department we'd have clocks that are order perfect. Anyway, if you don't know me, I'm Ivan Deutsch, and our TA for the course is here, Gopi. We're on leader on. Best I could do. But we just call him Gopi. And Gopi's going to be videotaping the course. The course will be, these lectures will be available online for you to review. Let me begin by just telling you how the information about the course is going to be distributed and how you access it, and a little bit about the requirements, etc. So this is going to be a paperless course, so all the materials will be available to you through the course website. And you can reach it, you can just Google us or go to the department's classes schedule, and it's linked there, or you can just write it down right now, the URL. Okay? But you can find it, and if you can't find it, just email me. So let's see, there's a few things I'd like to discuss in terms of the organization of the course to get started. Firstly, it's crucial that you've had, in order to take this course, the equivalent of the course here at UNM 491 and 492. That's our undergraduate level, senior level quantum mechanics. One way to get a feel for if you're not exactly sure if you're prepared for this course or not, I prepared here at the very bottom where we have our problem set for the course, a little diagnostic homework that you can see. I mean, yeah, it's okay. I mean, this is not going to be graded or anything. It's really for you to get a sense of, you look at this out, well, boy, this I don't know what any of this stuff is, or the vast majority of this just doesn't, you might think this course isn't for you, okay? But on the other hand, I do know the nature of the way physics education goes is we do subject matter and then we kind of do it again. So there's going to be a lot of overlap in some ways between what's happening, especially in this first semester, and what you saw in your senior level quantum mechanics classes. So we'll be sort of reintroducing all those concepts again, but at a fairly rapid rate and with more sophistication added on. The second semester of this course is really much more advanced and will probably cover things that you haven't seen at all in your undergraduate courses. Okay. So let's see, a few administrative details. We have, associated with the course, we have a problem session, which is currently scheduled at an ungodly hour. We're here, gosh, and who gets up for this course at 9:30, then we're going to have our problem session at 7 p.m. No, we're not going to do that. So, I will send around a little doodle poll to try to find another time that we can all have this problem session. It's going to be a challenge of about 15 people. We'll see if we can find a place, and then we have to find a room, because there's always Starbucks, but anyway, we'll figure it out, okay? We won't, we'll try to find the right time for doing that. I think that actually the best day to do that will probably be Friday. So the way the course is going to be organized is that homework will be distributed on the web, on the course website on Tuesdays, and then it will be due the following Tuesday in class. So my guess is it would be best to have the problem session on Friday so that we have the weekend to work on it, and then I'll have an office hour on Monday where, you know, those last minute panic questions can be answered, and then homework will be due on Tuesday. That sound reasonable? So we'll shoot for that. What do your Friday mornings look like right after the chair seminar? Anybody have anything at 10 o'clock on Friday? Oh, that would be terrific. Okay, so that's our tentative time, 10 o'clock Friday morning. And I'll see what we can do in finding a room. Maybe there's nothing in room 5 after the chair seminar, which would be just perfect. We'll also try to find a time available for office hours that Gopi will hold an office hour as I will as well. All right? So in terms of the grading, there will be homework pretty much every week. And it'll be about 3 or 4 questions. There will be 2 exams during the semester, sort of a little bit before fall break and a little bit before Thanksgiving. Dates not yet determined. Those will not be in-class exams. We'll try to schedule a time in the early evening to take the class so that we're under less time pressure. And then there is a final exam. I haven't looked at the date and time of that exam. Those are already scheduled by the university. So final exams are tied to the hour at which the course is taught. So the course is taught Tuesday and Thursday at 9:30, then there is a slot for the final exam. So we'll look whenever, we'll get to that. Let's see. There is no required textbook for the course because I'm a pretty idiosyncratic guy, as you'll get to know throughout the year, and I like to do things my own way. So what that means is that I will be distributing lecture notes for the course. I don't promise that they will be available before the semester, before the lecture, because one of my idiosyncrasies is that I think taking notes is a good idea. I mean, everybody should do what they like, but I find the process of trying to write something down helps me to learn material. So you try it. So if you're just kind of zoning out, looking at the notes, it's not always registered so well. So I won't always have the notes, but sometimes it's up to you. So you can download them. They're all in PDF format, and they look like this. Okay. And once we process the video, they'll be posted here. The lecture will be linked here as a podcast, so to speak. But obviously, it's good to have books. Books are your reference, and it's good to see different perspectives. I mean, books are expensive, though, so it's not sort of up to you to some degree what investments you want to and are willing to make. I've written down 3 books that sort of capture different pieces of what I'm going to be covering in this first semester, which is why I didn't pick any one of them. I'd say, if you want to have one book, a really great book is the book by Sakurai, but it's really kind of more for the latter part of this course and then for 522. It doesn't cover as much of the intro material as I will. The book by Cohen-Tanuji, et al., everyone calls it Cohen-Tanuji because no one remembers poor you and Lau. I speak French, I don't even know how to pronounce that name. But anyway, it's, well, I was a postdoc in France, and Claude Cohen-Tanuji taught at something called the College de France, which is college for other professors, basically. And it was something that I think was set up by Napoleon for the bourgeoisie to be continually educated, and they can come in and hear about whatever the intellectuals were talking about. But so people, I guess, will go in and talk to the social scientists, but the only people who go into the physics lectures are other physicists who you'd go to this, and you would say you'd go to church and you'd listen to the Pope. That was going to do G, and in the audience were all the other big professors and the bishops. Anyway, Going to do G is known as the Bible, and that was the point of that story. And it's organized in a very particular way. Some people hate it, some people love it. It has these there's the main part, and then there's the complements, and it's hard to organize, but it's got everything in it, and it's a good thing to have. There's a lot of worked out problems. It's a 2-volume set. I think the first volume is kind of better. So if you could afford it, get these 2 books. The book by Merzbacher is an old book, but it was, I don't know, redone about 15 years ago. It's kind of got everything in it, both the elementary and the advanced topics, so it kind of combines these 2. But I feel like the way the book was written is that he took each chapter was stapled together, and then he threw it up in the air, and then at the end he decided to bound it in some random order because, so, as you can see, I like to do things my own way. But in any event, there's many references, and I certainly recommend having some other textbooks on hand as references to get different perspectives, not just mine. All right? The tentative syllabus for the course is listed here. We'll see what we do. I expect we'll get through all of this material. My plan for the set of lectures is already sketched out, to be modified as things go. All right? So that's what's on the agenda. All right. Anybody have any questions, concerns?
So we don't have a lecture the Tuesday before Thanksgiving?
We won't. So there are some days that I will be traveling. I know that's one of them. Occasionally, there may be something else that comes up, so I do have some responsibilities from time to time, and I try to avoid accepting invitations that overlap with our lectures, but sometimes I will be traveling, and if we won't have lecture, we'll try to make it up at some other hour. Okay? All right, great. So let's get started. All right, so just get my notes here. So the first thing I want to discuss is, quantum mechanics is a pretty varied subject. What is quantum mechanics about? Well, the subject has really expanded in the last century. We just passed the 100-year anniversary of the Bohr atom. The Bohr model of the atom was introduced in 1913. So here we are in 2014. So originally, and I'd say what the majority of quantum mechanics quantum mechanics got its birth. And what many physicists of my generation and before always thought about what quantum mechanics was about talking about the structure of matter. So that might include, the birth of it was atomic structure, atomic physics, and quantum mechanics were one and the same. And quickly, of course, you get a couple of atoms, and then you talk about molecules. And from there to a much broader subject of condensed matter. So talking about all of that structure of all of matter, common matter, if you like, is a major structure, a major topic of quantum mechanics, and in some courses this is all you study. Of course, we then get into the subatomic regime, whether we talk about nuclear physics or even particles, subatomic particles, subnuclear particles, and of course the fields themselves. So one should expand this subject beyond matter, and the study of quantum fields is of course an important topic within the study of quantum mechanics. Now, of course, the way I describe all of these things, you can think about this really as the kinematics. It says that there is this structure, but it doesn't describe anything about the dynamics. And quantum dynamics is a subject that often and traditionally has gotten short shrift. And that's because traditionally it was very hard to control quantum dynamics. Natural systems in the world are typically occurring in such a way that what we'd say is these dynamics are incoherent, in a way that we'll come to understand a little bit later on in the course. And we typically, traditionally, when one learns about quantum dynamics, it's all kind of couched in terms of Fermi's golden rule and a rate equation for jumps, quantum jumps for absorption or emission. But there's a whole world beyond that, the world of coherent quantum dynamics and what that's about. And that's a subject we'll spend quite a bit of time discussing a little bit later in the course. But quantum mechanics, and why many of us have been fascinated by it, is not just about what is the structure of matter and fields and how they evolve in time, but there are some, of course, deep foundational issues. So it's the foundations of physical theory. Maybe I should go a little higher here. It's such a short. There we go. Let's go up here. So there are some very deep questions that reveal themselves in thinking about quantum mechanics. We have fundamental questions. Is physical theory deterministic? Versus random? We have the question is whether things happen in the world independent of us. Are they objective? Or are we in any way at the center of it? This is a discussion we continue to have, continues to be at the heart of our understanding of what we mean by quantum mechanics. Are things objectively real, or in some ways subjectively real? And that is the whole term real. This notion, is there a notion of local realism where an object has a property unto itself that is objectively real? And if not, what the heck are we talking about? What is even the alternative to that? So of course this is what motivates many of us to continue to probe and examine the nature. And these issues are not independent of these. The way in which we understand the structure of matter and fields is intimately related by the nature of the physical theory itself. And yet there's another stream that has become very prominent in the last, 80 years, and that's technology. So, ranging from things like material science, optical science, communications, computation, and the general understanding of information itself. All of these are part of the description, require a deep understanding of the quantum world. In fact, this latter subject, which is the subject of my own research interest, tied into optical and atomic physics, again draws very deeply on all of these issues in the foundations of quantum mechanics. Are many of us who worked in this field, our motivation was to understand the foundations of quantum mechanics, but in the process learned that maybe this had something to tell us about information theory itself. So the interaction between those has been a fascinating subject and continues to be. So we're going to touch on all of these things throughout the course of the academic year. This stuff may seem a little sexier, but to really understand all of it, and it's important as physicists to have all of these foundations as well. We best understand what the heck is a molecule? What's the Born-Oppenheimer approximation? These are things that are forgotten because they're not sexy anymore. We all want to learn about Bell's inequalities. But we better understand something if we're going to do astrophysics about the spectra of atoms and molecules. Want to understand the universe. We're going to be graduate students in physics. We should understand the structure of matters and fields. So we'll be spending quite a bit of time on that as well. So that's sort of the big picture. And so let's get into it. Why is this a subject that is challenging? Well, obviously we have these crazy questions that underlie it, and we're getting to make sense of that. So what's the key idea? Well, I would say the most important idea that we want to understand at the most basic level is the notion of the probability amplitude. So, how are we going to motivate that? Well, let's just start thinking about the ideas of, well, some language here. We talk about events and processes. What do I mean by that? Well, what I mean by an event is, and this is pretty hand-wavy, I'll have to try to make this more precise in a little bit, is something that registers on a detector. A lot of semantics there. Think about what the heck that means, define that more precisely. It's a tough thing to do. It's part of the whole problem, why I'm not doing it yet. But we could just, you know, there's, I forgot where there's this famous law case where, you know, someone said, well, you can't define pornography, but you know it when you see it. It's the same thing with an event. It's hard to define it, but when you see it, you know that's what you mean. So let's just say I have some kind of photo detector that goes click. And I have some light field photons impinging on this detector, and this detector is in some kind of Geiger mode, and it goes click when a photon is detected, okay? This is our event. So, now this event, generally, we can't predict. If and or when the event will happen. It's generally a random event. Okay? Now, because we can't predict this event with certainty, what that means is we have to appeal to the ideas of probability. Probability is the calculus we use in order to deal with incomplete certainty. Okay? So probability is what we use when we have incomplete certainty of events. Now, I won't get into this too deeply, but again, the notion of probability is a tough one. Is probability a subjective notion? Or is probability an objective notion? There's kind of two schools of thoughts about that. There's what are called the Bayesians and the frequentists. The frequentists don't have a hero, so they don't have a name person associated with them. But the subjective probability school does have a hero, it's Bayes. And, well, that question of objective versus subjective probabilities is something we'll touch upon when we get more deeply into trying to understand what quantum mechanics means. But for the moment, I'll just say, if we have incomplete uncertainty, we assign our probability to an event. So, for example, suppose I have a 50-50 beam splitter. So here is a what? back in the old days was called a half-silvered mirror. And it is such that if I send this photon onto this beam splitter, that if I have two detectors on these two sides of the beam splitter, call this, that there is a 50-50 chance of this going click or this going click. Okay? That's what we mean by a 50-50 beam splitter. So what is true is that if I send this single photon onto this beam splitter, then either this detector goes click or that one goes click, but they never both go click at the same time. If I were to gate these outputs onto a coincidence counter and look for coincidence counts for two clicks simultaneously within the window of the photon, I would never see both go click. I'd see either this or that. And each one is a 50-50 chance of that happening if this is a 50-50 beam splitter. So this is a random a set of events. Okay, so this kind of looks like flipping a coin, right? A fair coin, you flip a coin, and if it's a fair coin, you have a 50-50 chance of it coming up heads or tails. However, there's almost nothing about this that's really the same as a coin flip. Why do we say that the coin flip is a fair coin? I mean, this is classical physics. If I flip a coin, I have Newton's laws. F equals ma works pretty darn well for the coin. Why do I not know whether it's going to come up heads or tails?
Initial conditions, you don't know those?
Right, there's missing information about the coin. The reason for a coin flip, the outcome is random because of, and this is an important point, missing information. For example, as Zeke said, what are some of the things we need in order to specify that trajectory of that coin? We need to know the initial condition. We need to know what all the forces and torques are. We need to know the air pressure, wind. We need to know the forces exerted by the surface in which it lands. In fact, if we're good enough, and I'm not anywhere near good enough, but I've seen someone who can always flip a coin to land heads. You have to practice a heck of a lot, but if you torque it just the right way with just the right force, it's going to make exactly the right amount of flips. And you can kind of see, you can cheat and catch it in the right place so it's going to land heads. But it's only random because we don't know everything. If we knew all of these things, plus Newton's laws, there's nothing random about the coin at all. That's not true about this. There's something fundamentally different here. In some sense, there's no information archive that if we could just peer in, and like this archive, it would tell us which thing is going to happen. And of course, this is the kind of thing that gets at the heart of the questions of the nature of the quantum world. Is there some local hidden variables, some hidden information that would tell us which of these things happen? We just don't know it, and that's why things are random. To our understanding of things, the answer is no. It's impossible. It's just actually inconsistent with experiments that we can test, like Bell's inequalities, that there is a local archive of information local to the photon itself, which tells it what to do in the same way as the coin. And that's a very odd thing. So, because there's no, for the quantum, there is no local hidden information. And that fundamental difference means that the way in which events happen in the quantum world is just fundamentally different from the way they happen in the classical world. So for example, this fact that there is a local hidden information means that probability obeys different rules. So, the classic example of that is to think now of, consider the following. Let's say, so here's my beam splitter again. Here's my photon incident on that beam splitter. As we said, it could be reflected from that beam splitter, it could be transmitted from that beam splitter. But suppose now we set things up that we take these two possible trajectories that the photon goes and put in mirrors here. And so now this mirror reflects these guys. And so now they're come back to this point. And at this point, I put another 50-50 beam splitter. And now I put a detector here and another detector here. Okay? And let's imagine that this was a balance. So this is a Mach, what's known as a Mach-Zehnder interferometer. And let's imagine that it's balanced. That is to say, these two half lengths are equal. What's going to happen in that case? Well, it turns out in this situation, what we find if we balance these two arms of the interferometer is that detector A clicks with probability 1. Detector B, probability 0. Detector A always goes click. Every single time. B never receives a photon. How in the world is that possible? What this does is shows us that the laws of quantum mechanics defy the laws of logic. Because the laws of logic, the language of logic is probability. So classical probability
What do I mean by that?
Well, there are two paths that, or what I should say is, there are two processes, let's just call them generally processes, in this case paths, which lead to detector A clicking. Right? So there's two possible things that you might imagine logically. One possibility is that the photon came through, it got reflected, hit this mirror, got reflected at the mirror, and then got to the second beam splitter and was transmitted. Thank you. So this we'll call process one. That's one possible process that could lead to a click on detector A. Alternatively, it could be the case that, in fact, the photon was transmitted at the beam splitter, got reflected at this mirror, came up to the, and then was reflected. And then got to the detector. We'll call this process 2. Okay? Now, logically, what you would say is either process 1 happened or process 2. They're mutually orthogonal. That's how we're going to argue logically, right? And so if we want to say that either this or that happened, then the probability A clicks, if you have or, how do you combine probabilities if you have two different alternatives? You add them, right? If this or that happens, then the probability, the total probability is the sum of the probabilities, right? So that's the probability of process 1 happened plus the probability of process 2, because we have or. Okay. Now the probability of process 1 happening, well, there are two things that have to happen. This is equal to the probability of reflection at first beam splitter and probability of transmission at the second beam splitter. Right? And how do you combine those probabilities?
Multiply.
You multiply them, right? So in this case, that would be, there's a half and a half, or a quarter. Okay? And the probability for process 2 happening is the same kind of thing. It's the probability of transmission at the first, and then reflection at the second. And so that's a half and a half times between quarters. So classically, logically, we would say the probability that A goes click is this or that, which is a half. wrong answer. That's true. That's logic. And if that. But in fact, that's not the case. Because quantum mechanics doesn't operate under these intuitive laws of logic. It has its own calculus. Okay? So, that brings us to our key idea, the probability amplitude. What the rules of quantum mechanics tell us, so quantum mechanics operates under its own law. And what we have said is that if we have maximum knowledge about the state of a system, like the photon, we assign not a probability, but a probability amplitude. Which I might generically call psi. To the system. And psi is a complex number. The magnitude of this, which is less than or equal to 1, and the phase is arbitrary. If you're rusty on your complex numbers, you better review them. And the rules of quantum mechanics say that if there is an event, we assign a probability amplitude to that event. The probability of the event is then given by the square of the amplitude. This is the so-called, the famous Born rule. And this is the whole story. So, the counterintuitive behavior that we see in the interferometer follows what I'm going to call Feynman's rule. Of course, Richard Feynman was one of the greats of the last century in developing quantum field theory and our understanding of quantum physics as a whole. And Feynman's rule, let's see how I want to state it. Yeah. So, if two processes lead to the same event, and the processes are indistinguishable. And I'll explain what that means in a moment. Then the total probability amplitude for the event is the sum of the amplitudes. Okay. So, what that means is that whereas classically, if we have logical OR, we said we added probabilities. Quantum mechanically, if we have logical OR, we don't add the probabilities, we add the probability amplitudes. So that if there is an amplitude, a complex number associated with detector A clicking, that total amplitude is the sum of the amplitudes for the two. The logical OR now involves the amplitudes rather than the probabilities. Which means that the probability for A to happen according to the Born rule, well, that's the square of the amplitude associated with that, which is equal to that, which is equal to the number times its complex conjugate. That's how you get the magnitude squared of a complex number, which is equal to psi 1 squared plus psi 2 squared plus psi 1 star times psi 2 plus psi 2 star times psi 1. This, of course, is the probability for process 1, and this is the probability for process 2. So if we contrast that to what's written on the backboard, the probability for event A to happen is not just the sum of the probabilities of the two distinguished, the two alternatives, but involves something else. And this is quantum interference. This, of course, this quantity itself, probabilities are still probabilities. Probabilities are real numbers. They are between 0 and 1. Each one of these numbers is complex, generally, but this is the complex conjugate of this. And a number plus its complex conjugate is equal to twice the real part of that number. So this is a real number. But that real number can be positive or it can be negative. So, what we have here then is for the balanced Mach-Zehnder interferometer, for event click at A, what one finds is that this number is negative. It's negative a half. So that whereas P1 plus P2 here, according to what's written on the backboard, is a half, this is equal to minus a half. So that the total probability for A to go click, oh, it's the other way around. Sorry, this is head, right? This one's positive. This is 1. pardon me. Whereas for event click at B, this thing is negative. So the probability for B is 0. This is what we would call constructive interference. And this is destructive. So that's, in some sense, all of the mysteries of quantum mechanics, all the strangeness of quantum mechanics really is here. It's the fact and the idea that if you have different processes that lead to the same final outcome, you can't think about one or the other as we do classically, logically. We have to think there's a potentiality, there's a possibility that this or that happened. And to each one of those potentialities, we assign an amplitude. And then to get logically the total probability for the outcome, the logical OR, we add the amplitudes and then square it to get the total probability. And the result of doing that is that we will get these cross terms. We will get these interference terms. And those interference terms defy logic. Okay. Now, there's a point that one term that I threw out here, which is indistinguishable. Indistinguishability is important here. So processes are said to be indistinguishable if there is no information stored anywhere which tells us which process happened. So if, in principle, there is something that tells which of these processes happened, then the processes are no longer indistinguishable. And in that case, they no longer interfere. So if the processes are distinguishable, as opposed to indistinguishable, well then those two alternatives no longer interfere with one another. So for example, let's draw our Mach-Zehnder interferometer again. So here it is, the mirror. This guy goes along this path, that path, reflected, reflected. We have eye detectors. If it was balanced, what we just described was a situation that all the photons would come out here and they've never come out here. But suppose I modify this a little bit and I place in the path of one of these arms of the interferometer a Pockle cell. So a Pockle cell is a crystal which, when light passes through it, develops a voltage across it. Okay? So I can put a little voltmeter across the Pockle cell. It's a transparent crystal. the light passes through it. But when it does, there is an interaction between the light and the crystal such that a voltage develops across it. Well, in that case, if voltage develops across this crystal, we know that the photon went along this path. So what do you think happens in that case?
So 50-50.
50-50. In that case, because this now is distinguishable paths, this goes 50% of the time this goes click, and 50% of the time this goes click. Because then, if I don't have two paths, if I don't see voltage here, then I know I have process 2. And when I have process 2, there's only one possibility. It went along this path. And then when it goes along that path, it flips, 50-50. If I do see voltage here, then I know process 1 happened. And if process 1 happened, it went like this, and then when it gets there, and there's no two indistinguishable alternatives which can either constructively or destructively interfere with one another. All right. Now, of course, the notion of interference has its birth in classical physics. We're familiar with the notion of interference from the ideas of classical waves. So if I look at this interferometer, for example, I can think about this as an interferometer that interferes classical electromagnetic waves. So suppose I have an electromagnetic wave, and suppose I have the electric field associated with, say, a linearly polarized plane wave. So my electric field, say, along some axis as a function of time, say, is got some linear polarization, E naught cosine kx minus omega t, which we often write as the real part of e to the I kx minus omega t. This we often call the complex amplitude of the electric field. It's a complex number, but the field itself, which gives rise to the forces, is the real part of that. In the case of the classical electromagnetic theory, we introduce these complex amplitudes for convenience. The fields are fundamentally real. We do that because it's easier to deal with exponentials than sines and cosines. But we could do it always in terms of sines and cosines. Excuse me. Nonetheless, this is a convenience, and it gives us sort of the basis for where some of this stuff comes from. Of course, we know the intensity of the field, which say is the time average of the electric field, is given here by, most proportional to this. It's got some epsilon naughts or something like that, but basically that. So this kind of has some flavor of the Born rule in it. The intensity is the square of the amplitude. And of course, sort of the flavor of a part of the Feynman rule, which is that if I can have linear superposition. That is to say, if I have two waves impinging at the same point, the total intensity at that point is not the sum of the intensities of the two waves. It is the sum of the amplitudes, the sum of the fields. So that if I have that situation, my E total is the sum, or the amplitude is the sum of the two fields. And then the total intensity is the total electric field amplitude squared, which of course is the sum of the intensities, and then in interference terms, coming from the interference of those waves. So this is familiar in some sense, but yet quite completely different. Because in the case of the classical field, if I send in a wave at this beam splitter, half of the intensity is reflected and half of the intensity is transmitted. But if I have a single photon at here, it's not like half of the photon is reflected and half of the photon is transmitted. It's that there is this corpuscle, this quantum, this particle-like thing, which is either completely transmitted or completely reflected. And if we were to try to look for both detectors clicking simultaneously, we would never see that. So this classical idea, what would happen here, if I said it in a laser beam here, where half the intensity is transmitted and half of the intensity, is reflected and half of it is transmitted, well, that's in some sense an average phenomenon, right? Because if I were to look at this, what I would say is that I might think about this as some random stream of particles impinging on here, which click, sometimes go here and sometimes go here, okay? On any event, I either see a click here or a click here, never both. But it's a 50-50 chance, right? So what I would see if I were to do this experiment is what? Suppose I have n photons impinging on this beam splitter. And I want to know what is the probability of seeing n sub a photons at this detector. What would you say? Well, no, I mean, any one photon is a half, but the problem with seeing n of those is what? Yeah, that's true, if I had, and we'll come to that in a moment, in the limit that NA goes to infinity. But let's think about this for a moment. Flip a coin, that's what's going on. I have n flips of a coin. There's some fluctuations there that doesn't square root n. It's a binomial distribution, right? Remember that from your probability theory. There's a number of different ways I can choose n sub a photons out of n photons. This probability times a half to the power na times a half to the power n minus n sub a. Right? That's a binomial distribution. This is, n factorial over n a factorial n minus n a factorial. But as in the average number of photons I will see at this detector is what was suggested, this. On average, half of them will be transmitted and half of them will be reflected. But there will be fluctuations, as Monica suggested, about this, because this is counting statistics, right? That's the fluctuations associated with the binomial distribution. So the fluctuations about that, our uncertainty, if you like, will be equal to the square root of n times a half. Now, in the limit, as n gets very, very large, the fluctuations are tiny compared to the mean. Which means that if we were to do a very, 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 very large number of photon counts, what we would find is that the number we would detect on here would be n times the probability. So one way of thinking about this is there's a relationship between probabilities and fractions, frequencies of outcomes. And that's, in some sense, where the Born rule came from originally, although it's a little confusing because, as I say, that gives a sense that probabilities are objective. When in fact, that's not really the right way to think about it. But nonetheless, I could say that the probability becomes concentrated on the frequency of outcomes. So that the frequency of A here is equal to the number A over the total number, or I can think about this as the electric field coming out at port A over the total intensity. So if I think about the fraction, this is the fraction for frequency of the intensity that comes out one port or the other, that converges as n goes to infinity to the probability. And so the Born rule has its birth in thinking about interference of classical waves, but it's something deeper than that, and something that we're going to grapple with over the course of this year. And that's really the most important idea. But we're going to use all of this to talk about all the ingredients I discussed, the structure of matter, technologies, etc. So we'll get started with this next time. What we're going to do, starting for the next few lectures, is to review and make more sophisticated this amplitude calculus through the theory of Hilbert space. linear algebra, operators, all of that stuff. And we'll be doing kind of math for the next few lectures. All right? Very good. I'll be emailing everybody to try to determine the times for our office hours, etc. And I'll confirm that we will have our problem session on Fridays, but we'll start next week. All right? Have a good rest of your day. But I feel like the way the book was written is that he took each chapter was stapled together, and then he threw it up in the air, and then at the end decided to bound it in some random order because, like, so, as you can see, I like to do things my own way. But in any event, there's many references, and I certainly recommend having some other textbooks on hand as references to get different perspectives, not just mine. All right? The tentative syllabus for the course is listed here. We'll see what we do. I expect we'll get through all of this material. My plan for the set of lectures is already sketched out, to be modified as things go. All right? So that's what's on the agenda. All right. Anybody have any questions, concerns?
So we don't have a lecture the Tuesday before Thanksgiving?
We won't. So there are some days that I will be traveling. I know that's one of them. Occasionally, there may be something else that comes up, so I do have some responsibilities from time to time, and I try to avoid accepting invitations that overlap with our lectures, but sometimes I will be traveling, and if we won't have lecture, we'll try to make it up at some other hour. Okay? All right, great. So let's get started. Maybe. There we go. All right, so just get my notes here. So the first thing I want to discuss is, quantum mechanics is a pretty varied subject. What is quantum mechanics about? Well, the subject has... All right. Good morning, everybody. Good to be back here, knowing we're here in the Department of Physical Astronomy where all the clocks are always some random numbers. So let's get started. You'd think in a physics department we'd have clocks that are quarter perfect. I don't know. Anyway, if you don't know me, I'm Ivan Deutsch, and our TA for the course is here, Gopi. We're on leader on, best I could do, but we just call him Gopi. And Gopi's going to be videotaping the course. The course will be, these lectures will be available online for you to review. Let me begin by just telling you how the information about the course is going to be distributed and how you access it, and a little bit about the requirements, etc. So this is going to be a paperless course, so all the materials will be available to you through the course website. And you can reach it, you can just Google us or go to the department's classes schedule, and it's linked there. or you can just write it down right now, the URL. Okay? But you can find it, and if you can't find it, just email me. So let's see, there's a few things I'd like to discuss in terms of the organization of the course to get started. Firstly, it's crucial that you've had, in order to take this course, the equivalent of the course here at UNM 491 and 492. That's our undergraduate level, senior level quantum mechanics. One way to get a feel for if you're not exactly sure if you're prepared for this course or not, I prepared here at the very bottom where we have our problem set for the course, a little diagnostic homework that you can see. I mean, yeah, it's okay. I mean, this is not going to be graded or anything. It's really for you to get a sense of, you look at this, well, boy, this I don't know what any of this stuff is, or the vast majority of this just doesn't, you might think this course isn't for you, okay? As a podcast, so to speak. But obviously, it's good to have books. Books are your reference, and it's good to see different perspectives. I mean, books are expensive though, so it's not sort of up to you to some degree what investments you want to and are willing to make. I've written down 3 books that sort of capture different pieces of what I'm going to be covering in this first semester, which is why I didn't pick any one of them. I'd say, you know, if you want to have one book, a really great book is the book by Sakurai, but it's really kind of more for the latter part of this course and then for 522. It doesn't cover as much of the intro material as I will. The book by Cohen-Tanuji, et al., everyone calls it Cohen-Tanuji because no one remembers poor you and Lau. I speak French, I don't even know how to pronounce that name. But anyway, it's, you know, well, I was a postdoc in France, and Claude Cohen-Tanuji taught at something called the Collège de France, which is college for other professors, basically. And it was something that I think was set up by Napoleon for the bourgeoisie to be continually educated, and they can come in and hear about whatever the intellectuals were talking about. But, you know, so people, I guess, will go in and talk to the social scientists, but the only people who go to you know, the physics lectures or other physicists who you'd go to this, and you would say you go to church and you'd listen to the Pope. That was going to do, and in the audience were all the other big professors and, you know, the bishops. Anyway, Cohen-Tanuji is known as the Bible, and that was the point of that story. And it's organized in a very particular way. Some people hate it, some people love it. It has these sort of, there's the main part, and then there's the complements, and it's hard to organize, but it's got everything in it, and it's a good thing to have. There's a lot of worked out problems. It's a 2-volume set. I think the first volume is kind of better. So if you could afford it, get these 2 books. The book by Merzbacher is an old book, but it was, I don't know, redone about 15 years ago. It's kind of got everything in it, both the elementary and the advanced topics, so it kind of combines these 2. I'll see what we can do in finding the room. Maybe there's nothing in room 5 after the chair seminar, which would be just perfect. We'll also try to find a time available for office hours that Gopi will hold an office hour as I will as well. All right? So in terms of the grading, there will be homework pretty much every week. And it'll be about 3 or 4 questions. There will be 2 exams during the semester, sort of a little bit before fall break and a little bit before Thanksgiving. not yet, dates not yet determined. Those will not be in-class exams. We'll try to schedule a time in the early evening to take the class so that we're under less time pressure. And then there is a final exam. I haven't looked at the date and time of that exam. Those are already scheduled by the university. So final exams are tied to the hour at which the course is taught. So the course is taught Tuesday and Thursday at 9:30, then there is a slot for the final exam. So we'll look whenever, we'll get to that. Let's see. There is no required textbook for the course because I'm a pretty idiosyncratic guy, as you'll get to know throughout the year, and I like to do things my own way. So what that means is that I will be distributing lecture notes for the course. I don't promise that they will be available before the semester, before the lecture, because one of my idiosyncrasies is that I think taking notes is a good idea. I mean, everybody should do what they like, but I find the process of trying to write something down helps me to learn material. So you try it. So if you're just kind of zoning out, looking at the notes, it's not always registered so well. So I won't always have the notes, but sometimes it's up to you. So you can download them. They're all in PDF format, and they look like this. Okay. And once we process the video, they'll be posted here. The lecture will be linked here. But on the other hand, I do know the nature of the way physics education goes is we do the subject matter and then we kind of do it again. So there's going to be a lot of overlap in some ways between what's happening, especially in this first semester, and what you saw in your senior level quantum mechanics classes. So we'll be sort of reintroducing all those concepts again, but at a fairly rapid rate and with more sophistication added on. The second semester of this course is really much more advanced and will probably cover things that you haven't seen at all in your undergraduate courses. Okay. So let's see, a few administrative details. We have, associated with the course, we have a problem session, which is currently scheduled at an ungodly hour. We're here, gosh, and who gets up for this course at 9:30, then we're going to have our problem session at 7 p.m. No, we're not going to do that. So I will send around a little doodle poll to try to find another time that we can all have this problem session. It's going to be a challenge of about 15 people. We'll see if we can find a place, and then we have to find a room, because there's always Starbucks, but anyway, we'll figure it out, okay? We won't, we'll try to find the right time for doing that. I think that actually the best day to do that will probably be Friday. So the way the course is going to be organized is that homework will be distributed on the web, on the course website on Tuesdays, and then it will be due the following Tuesday in class. So my guess is it would be best to have the problem session on Friday so that we have the weekend to work on it, and then I'll have an office hour on Monday where those last-minute panic questions can be answered, and then homework will be due on Tuesday. That sound reasonable? So we'll shoot for that. What do your Friday mornings look like right after the chair seminar? Anybody have anything at 10 o'clock on Friday? Oh, that would be terrific. Okay, so that's our tentative time. 10 o'clock Friday morning. And